When a wave is emitted from a moving source, the wave will get squashed up ahead of the source and stretched out behind the source. Let's take a car horn as an example. So here we've got a car and it's sitting still and it honks its horn and the sound waves emit from it like this. You can see that the wavelength is exactly the same all around the car. The car horn is going to sound exactly the same wherever you are relative to it. But now let's say that the car starts moving while it's honking its horn. This happens to the waves being emitted. You can see that the waves in front of the car have been sort of squashed up a bit, and the waves behind the car have been stretched out a bit. So they've got a shorter wavelength in front of the car and a longer wavelength behind the car. Now, the speed of waves never changes in the medium that it's in. So if the wavelength has changed and the speed is the same, that means the frequency must also have changed. So what this means in terms of the car honking is that in front of the car, so when the car is coming towards you, the car horn will sound a bit more high-pitched. But when it's moving away from you, because the sound waves have stretched to a longer wavelength, a lower frequency, they will sound more low-pitched. So let's have a look at an example. I actually found a really nice video on YouTube of this. I'll link to it in the description if you want to watch it a few times. But you should be able to notice it's a video of a car honking its horn driving past the camera. And you should be able to notice the pitch of the horn go down as it goes past us. It will sound high-pitched as it's coming towards the camera and then low-pitched as it's going away from the camera. Let's check that out. Did you hear it? Did you hear it go down in pitch as it drove past us? When it's coming towards us, it's high pitched, going away, it's low pitched. That's a really, really good example. It's a great video. I'll link to it down in the description, like I said, if you want to watch it a few more times. Cool. This is called the Doppler effect. The Doppler effect describes how a moving source emitting waves will stretch or squash them, depending on whether it's coming towards or away from us. So what does this have to do with galaxies and space? Well, galaxies emit light. And light is a wave. So if a galaxy is moving away from us fast enough, the waves, the light waves coming from that galaxy will get stretched out. They will get a longer wavelength. Now, since red light has the longest wavelength in the visible spectrum, we call this effect redshift, because any visible light will be shifted a bit towards the red end of the spectrum. It's not a perfect way of thinking about it, but that's why we call it redshift. Because the galaxies are moving away from us so quickly, the light waves get stretched out and then become longer wavelength, redshifted. We can actually use redshift to work out how fast the galaxies are moving away from us as well. And it turns out that the further away a galaxy is, the faster it is going. And that is good evidence for an expanding universe, and also good evidence for the Big Bang Theory. So there you go, redshift is good evidence for the Big Bang Theory, because the further away a galaxy is, the more redshifted it is, therefore the faster it is going.